Welcome to 93rd Theoretical Physics Colloquium by Professor Margaret Carrington from Brandon University in Canada. She received her PhD at State University of New York at Stony Brook in 1989. She had several postdoctoral positions at the University of Minnesota and Winnipeg University. She held von Humboldt Fellowship at Regensburg University before she became a faculty at Brandon University in '97. And since 2003, she is also an adjunct professor at the University of Manitoba. Her interests include relativistic heavy ion collisions, statistical fields theory, matter under extreme conditions, effective actions, non-perturbative methods in graphene and elsewhere, plasma instabilities, and isotropic QCD plasmas, and many other things. And today she is going to talk about early time gluon fields in relativistic heavy ion collisions. And with that, I'll give the microphone to Margaret.
Great, thanks a lot, Igor. Okay, yeah, so I am going to talk about some work I've done in the past couple of years together with collaborators at the National Center for Nuclear Research in Warsaw. Very touchy. Okay, so what we're interested in is the first phase of the matter that's produced in a heavy ion collision, which is called the glasma. This is the phase that's the least well understood, but it's crucial because it provides the initial conditions for the subsequent hydrodynamic evolution. So I'm going to discuss in very general terms the structure of the calculation that we did. We used a Colour Glass Condensate effective field theory approach, and I'm going to describe only in very general terms what that means, and then as quickly as possible move on to the results. So this is sort of a list of the highlights of what we've calculated. We've looked at isotropization in the glasma. We've looked at azimuthal asymmetries in the momentum distribution and also spatial azimuthal asymmetries. We've calculated the angular momentum of the glasma, which is experimentally relevant these days. And then most recently, we've looked at the momentum broadening of hard probes. Okay. So this is a sketch of the different stages in the evolution of a heavy ion collision. The Colour Glass Condensate, or the CGC, is the high energy density, largely gluonic matter that's associated with the wave function of a high energy hadron. So this is the initial state in the collision, and that's what you see on the far left side of the diagram. So then after the collision, these CGC fields get transformed into glasma fields. So you have initially longitudinal color electric and magnetic fields that are oriented along the beam axis. So that's the glasma phase. And then the glasma will eventually decay into a quark gluon plasma that is described by some version of hydrodynamics. And then the plasma itself will decay into a hadron to get gas, and it's those hadrons that reach the detector. So this is a space-time diagram that shows the same information in a different way. So the vertical and horizontal axes are the time and the Z axes. So in our notation, the collision axis is the Z axis. And then the diagonal lines are the light cone axes, and the light cone variables are defined here. X plus is equal to T plus or minus Z over √2. So then the idea is that the collision takes place at the origin of the diagram, so where T and Z are equal to 0. And then in the lower part of the diagram, where not very much is happening, this is where the two ions are approaching the collision point. And so in our notation, the first ion moves in the positive Z direction. So it's moving along the X plus axis. It's moving along here. Whoops. Great. And the second ion is moving in the minus Z direction. So it's moving along the X minus axis here, approaching the collision point. So the triangle in the top half of the figure is called the forward light cone. And this is the region of the space-time that's causally connected to the collision. So all of the post-collision matter is living up there in the forward light cone. And then the different colors represent the different phases that I showed you on the previous slide. Okay, so as I said, what we're trying to do is describe the very early time dynamics of the heavy ion collision. So this is the phase that's not very well understood, in contrast to the hydrodynamic phase, which has been studied intensively for many years. And hydrodynamic models are very successful at describing properties of the quark gluon plasma. But the initial conditions come from this glasma phase. And then more generally, we would like to understand better the transition between the two phases. So the idea here is that at very early times, we know the system is governed by a microscopic theory of non-abelian gauge fields, which is valid arbitrarily far from equilibrium. And then at some later time, you arrive at the hydro regime. And there you're talking about a macroscopic effective theory. It's based on universal conservation laws, and it's valid somehow close to equilibrium. So these two things are very different from each other, and we want to know better how one gets from one to the other. So everything I'm going to be talking about today, you can find more details in these papers. Okay, so we used a color glass condensate effective field theory approach, and I'm going to describe just in very, very basic terms what that means. So the method is based on a separation of scales between valence partons that have large nucleon momentum fraction, and then gluon fields that are small x but large occupation numbers. So these gluons are in the saturation regime, which means that their distribution functions are controlled by the saturation scale. So then the idea is that the dynamics of these gluon fields is determined from the classical Yang-Mills equation, where the source is provided by these valence partons. Okay, so on this slide, I'm just giving you some notation. So we work in different places in light cone coordinates and Milne coordinates, and I'll explain why in a second. So the light cone coordinates are there at the top of the slide, and that's the definition I gave before. When you work in Milne coordinates, instead of t and z, you use the proper time and the space-time rapidity, which are defined there. Then in both cases, we also have two coordinates that span the transverse plane. So these are just x and y normal Cartesian coordinates. Okay, so at the bottom of the slide there is the space-time diagram again. And here you see the two sources, J1 and J2, that are coming into the collision. So the form of the source function is given there in the middle of the slide. So rho 1 here is the charge density of the first ion. It depends on x minus because it has a small width across the light cone, which is you can see here in the figure. It doesn't depend on x plus or the light cone time, and this is called the static approximation. And what it means physically is that the lifetime of these valence sources is much longer than the lifetime of the small x degrees of freedom. Okay, so then the goal is to solve the Yang-Mills equation using this ansatz for the vector potential. So it looks sort of massively confusing, but the idea is that these theta functions separate the different regions in the space-time diagram. So the forward light cone where the glasma is living are all the terms that are proportional to the product x plus and x minus. And so when you look at the different terms, there are three functions. This function alpha, and then in the last line, alpha perp, has two components for the xy components. It's perpendicular to the beam axis, so it's living in the transverse plane. Okay, so there are three components to the glasma. And the reason that there are three instead of four, as you would expect, is just because of the gauge condition. And then the next thing you notice is that they're written in Milne coordinates. And the reason for that is in a relativistic collision, we expect that boost invariance should be a good approximation. So we want to work in Milne coordinates where we can use functions that are independent of the rapidity. So then the rest of the ansatz is these two pieces, beta 1 and beta 2. And so beta 1 is the one that lives over here on the left side of the diagram. So this is not part of the forward light cone. It's before the collision. This is the potential of the first ion, the one that's incoming along the positive z-axis. And likewise, on the right side of the diagram, you have the potential that comes from the second ion. Okay, so this is just a basic description of the method that we're using. So starting from the valence sources, you can solve the Yang-Mills equation to get the pre-collision potentials. So I just wrote down the solution here for reference. The only thing that you need to kind of remember is that if you start from the sources, you can solve the Yang-Mills equation and get out the pre-collision potential. Similar equation for the beta 2 function. And then at the bottom of the page, I'm just repeating what I said before, that this source rho 1 is independent of the light cone time x plus because it's in the static approximation. It depends on x minus because it has this small and finite width across the light cone. So that's necessary to keep it for technical reasons until the end of the calculation, at which point we take it to 0. which is what I'm saying next here. So once you have your pre-collision potentials, the beta 1, beta 2, you can find the glasma potentials at the initial proper time. And you do that by applying these boundary conditions. And the boundary conditions can be derived by imposing continuity conditions across the light cone. So remember, the ansatz has got these theta functions that are separating different regions of the light cone. Okay, so once you have the initial glasma functions, you don't want just to know what the glasma functions are at time tau equals 0. You want them at some finite proper time. And so then the idea is to do an expansion around tau equals 0. So since you're only interested in very early times, you could use the proper time as an expansion parameter. So then, of course, you have to solve for the coefficients of the expansion. And you do that by requiring that the vector potential satisfies the sourceless Yang-Mills equation. So at the end of the day, then you obtain these coefficients of the expansion in terms of the initial potentials and their derivatives, which you know in terms of the pre-collision potentials. Okay, so this is sort of a grand summary of the whole thing. You start from static valence parton sources, you solve the Yang-Mills equation, and you get these CGC pre-collision fields. Then by imposing boundary conditions, you get the initial glasma fields, and then using a proper time expansion, you get the glasma fields at some finite proper time. Okay, so the problem with the scenario then is that way back at the beginning, the color charge distributions are not known. So the CGC trick is to assume that you have a Gaussian distribution of color charges in each nucleus, and then a product of sources gets replaced by its average over this distribution. So then you use the fact that the average over a Gaussian distribution of independent random variables is the sum of the averages of all possible pairs. So in field theory, this is just known as Wick's theorem. And then the idea of CGC is to say that the local fluctuations are proportional to the surface color charge density, which we call mu. So that's what I wrote down here. And then there's an analogous expression for the second ion. Okay, so the next step is that what we want to calculate is not correlation functions of source charge densities, but we want to calculate correlators of these pre-collision potentials. So we use the glasma graph approximation, which says that you can apply Wick's theorem directly to the potentials. So this is an approximation that's been used by many authors, and it's been studied in lots of papers. We were able to show in our first paper that for our calculation, making this approximation doesn't have a very drastic effect on the results. Okay, so this is the expression for this correlator of two pre-collision potentials, which we call B. It depends on two different regulators, these parameters M and QS. M is an infrared regulator that can be associated with the confinement scale. And QS is an ultraviolet regulator that we set to be equal to the saturation scale. So of course you would like to show that results don't depend weakly on the choices that you make for these scales. We make sort of a standard choice, but you would like to show that they're only weakly dependent on these numbers. And I'll show you some results where we've investigated that later on. Okay, so the dots here on the right-hand side, that means we've kept terms up to second order in the gradient expansion of the source charge function. And there's kind of like another half a page of terms, so I didn't write them down just because they're sort of messy to look at. So in order to understand what's going on there, I have to tell you what's the form of the color charge density function that we used. So we used the two-dimensional projection of a Wood-Saxon potential, which is what I wrote down here. So on the right side, this is more or less a recognizable Wood-Saxon form. There are two parameters, Ra and little a, which are the radius and the skin thickness of a nucleus of mass number A, and we chose standard values for those numbers. Then on the right side, there's a normalization function, which is defined so that at the center of a lead nucleus, the density is normalized to the MV scale. So this MV scale is proportional to the saturation scale. But the exact value of that proportionality constant isn't known. And so we made sort of a conventional choice. But the fact that this proportionality is not known tells you that when we obtain numerical results for something like the energy density, You can really only consider this to be an order of magnitude estimate. However, if you look at something that is determined by ratios of elements of the energy momentum tensor, they're going to have a much weaker dependence on this scale. Okay, so now I can tell you how the gradient expansion works. So this is a plot of mu, that's the red line, and the first two derivatives, so the green and the blue. And the black dotted line is a plot of this parameter delta, which is what we're assuming to be small when we make the gradient expansion. And the vertical line is the value of r for which delta equals 0.75. So what you see from this figure is that the derivatives are appreciable only in a very small region at the edges of the nucleus. And so what that means is if you're calculating some observable where the integrand gets large contributions around the edges, then you're going to have to be very careful about how you use the gradient expansion. But if you're calculating something that's not sensitive to the behavior around the edges, then there shouldn't be any problem. And so I'll give you some examples of this when we go farther on. Okay, and so finally, I can now tell you how we take into account collisions with non-zero impact parameter. So if it's not a head-on collision or a non-central collision, that we can describe that. We have the two different ion charge densities, and we can translate the average coordinate of the two by plus or minus b over 2. So separating them in different directions, then we get an impact parameter of b for that collision. Okay, so this is kind of my grand summary of the theory. We solve the Yang-Mills equation by averaging over a Gaussian distributed valence sources and get correlators of pre-collision fields. So then we get the glasma field correlators by using boundary conditions and a tau expansion and then solving the sourceless Yang-Mills equation. And then once you've got the glasma field correlators, you can calculate from them the correlators of glasma chromodynamic, electric, and magnetic fields. And from those, you can directly get observables. Okay, so I just should be clear at this point that everything I've described so far is not originally done by us. This has all been done by other authors in different ways over many years. I'm just describing how the method works. So what we did was we worked out a more efficient way to do these calculations, which allowed us to work up to 6th order in the tau expansion, whereas previous calculations were limited to sort of partial 4th order. And we've also calculated some interesting observables that had been considered before with these methods. Okay, so this is the same list that I gave you at the beginning. I'm going to go into more detail on these things now. And then finally, a last comment. There are obviously many numerical approaches to study initial dynamics. Our method is fully analytic. And so one advantage of that is it allows you to get complete control over the approximations that you're making and the sources of error. And in principle, at least, you can systematically extend the calculation to arbitrarily high orders. But of course, the analytic method has its own inherent limitations. Okay, so I want to talk about the isotropization of the glasma first. And so to explain the idea, this is the energy momentum tensor at the initial time of the collision. So it has this simple diagonal form. The longitudinal pressure is the 2,2 component, and it's large and negative. So that happens because the system is produced initially far from equilibrium. So if the system is to approach equilibrium as it evolves, the longitudinal pressure has to grow and the transverse pressure has to decrease because the energy momentum tensor is traceless. Okay, so to see how that works, we look at this variable A. So in equilibrium, A would be 0 when PT is equal to PL, and it has an initial value of 6. So the figure shows A as a function of this dimensionless time variable. And we're looking at 3 different orders in the tau expansion. So when the times are very small, all orders in the expansion agree, as they should, of course. And as time increases, they start to deviate, which is what one expects. So what's important about the figure is that over the range of the expansion where we can trust the tau expansion, over the range of the independent variable where we trust the tau expansion, A is more or less uniformly decreasing, which tells us that the system is approaching isotropy. Okay, so in order to check that things sort of more or less make sense, we can repeat the calculation using a finite impact parameter. So what we should see is that if you have a smaller impact parameter, you've increased the region of overlap and the system should isotropize faster. And so that's what we see here in the figure. The red line is the curve I showed you before at order tau sixth, and the blue line is the result you get when you increase the impact parameter. Okay, so while I'm on this slide, I defined the reaction plane. It's defined by the collision axis and the vector provided by the impact parameter. So then in the transverse plane, when phi is 0, you're in the reaction plane, and when phi is pi over 2, you're perpendicular to the reaction plane. Okay, so this figure shows the same variable A in a different way. So these are contour plots of the value of A in the transverse plane, and time is advancing to the right. So what you see then is that the blue area is spreading out and filling out the plane, which shows you that the system is isotropizing more or less uniformly across the transverse plane. Okay, so before we go on, we can look briefly at the dependence of this variable A on the confinement scale and the saturation scale. So at the top of the slide here, I'm just repeating what I already said. When you calculate this correlator, you get this result that I showed you that depends on these two scales, the infrared regulator and the ultraviolet regulator. And so we know that these two scales physically are related to the confinement scale and the saturation scale. So we have constraints on how to choose them, but we would like to see that results are reasonably independent of the choice that we make, especially since the two scales are very close together. So that's what we see in this figure. This is that same variable A at order tau sixth as a function of time. And in the left side, we're looking at 3 different values of QS with M fixed to 0.2. And on the right side, it's the other way around, 3 different values of M with QS fixed to 2 GV. And so as you can see, the results have shifted a little bit, but it depends only very weakly on this scale. Okay, so another thing that's sort of easy to understand is radial flow. So the transverse momentum flow vector is the I0 component of the energy momentum tensor. And then you can characterize the radial flow of the expanding plasma by taking the radial projection of that flow vector. So the graph shows this quantity P as a function of the dimensionless time variable at 3 different orders in the tau expansion. So at lowest order, you get a linear increase with time. But when you look at the higher orders, then you can see that P is slowing down as the system expands, which is what you expect. So if you look just at the tau cubed result, it looks like it's sort of dipping down there. But when you include the tau fifth result, you can see that's an artifact of the expansion breaking down. And the physical result is that P sort of flattens out up to a value of about 0.5, which is again telling you where the tau expansion is breaking down. Okay, so the next thing I want to talk about is azimuthal asymmetry. So the basic idea here is if you have a non-central collision, then there's initial spatial asymmetry. But in a relativistic collision, you expect the spatial asymmetries to decrease very rapidly. And so that means that any anisotropy in the momentum flow could only develop in the first few Fermi over C. So that kind of isotropy then is sensitive to the system's property very early in its evolution. And in this sense, it provides us with direct information about the early stages of the system, which is what we want. Right, so I wrote down on the slide that the definition of the Fourier coefficients Vn, for people who are sort of familiar with this but can't remember how they're defined. If you've never seen it before, then you can just look at the last equation, and you can see from that that if there was no azimuthal asymmetry, the Fourier coefficients would be 0. So what we're looking for are deviations from 0. Okay, so this slide shows the first 3 Fourier coefficients as functions of the impact parameter. So if you compare with experimental values, V2 and V3 are sort of comparable. V1 is bigger than expected. But when you take into account that one usually assumes that anisotropy develops mostly during the hydrodynamic evolution, our results for all three of these Fourier coefficients are quite large. And then just a comment here, experimentally, the situation is fairly complicated because you don't know what the impact parameter is, and you don't know exactly where the reaction plane is. So our calculation doesn't correspond exactly to what is measured. So in order to sort of make sense of it, we can compare with spatial deviations from azimuthal symmetry. And so these can be characterized by calculating moments of the energy density. So now the figure shows the eccentricity E2 is the blue, the elliptic flow coefficient V2 is the green, and the ratio is the red line. So this is as a function of impact parameter at fixed time and rapidity. So what you're supposed to take away from this graph is the flatness of the red line. It's telling you that there is a significant correlation between the spatial asymmetry that you introduce with the geometry, which is then getting transmitted into the anisotropy of the momentum distribution. And that's interesting because correlations of that type are considered characteristic of the onset of some kind of hydrodynamic behavior. Okay, so next I want to talk about angular momentum. So to define the angular momentum of the glasma, we start off by defining this tensor M. And so the gradient of M is 0 because the energy momentum tensor is conserved. And that means you can define a set of conserved charges using Stokes' theorem. So in this equation, N is a unit vector that's perpendicular to the hypersurface sigma. And so the idea then is we want to choose N to be this time-like vector in known coordinates so that our charges are defined on a hypersurface of constant tau. So then you define the angular momentum in terms of the Pauli-Lubansky vector. And the result of that procedure is that the angular momentum per unit rapidity is given by this very simple expression. So it looks this simple because I assumed a symmetric displacement. So I move the two ions are incoming in the Z direction and I move them symmetrically apart in the X direction. And so that produces this form that looks just like R cross P as you would expect. Okay, so this is our result for the energy, for the angular momentum. So this is a function of impact parameter. So it looks sort of reasonable. It increases in magnitude as the impact parameter increases until you get to a point where the ions sort of start to miss each other and then it drops back down again. You can also check that the sign is correct based on the way that I displaced the ions. It's rotating in the right direction. And then at the bottom of the slide here, I put down a little warning. In this calculation, the dominant contributions to angular momentum come from the parts of the nuclei that are farthest from the collision center, because that's the way angular momentum works. And so as I was describing earlier, these are the parts of the nuclei where the gradient expansion is the least to be trusted, which means that the error bars on this graph are pretty big. Okay, so to see if this is sensible, we compare with the calculations of other people. So this is a calculation done for the angular momentum of an initial system of colliding ions. The shape of this result is very similar to ours. It's flipped over because there's a minus sign here. But the basic shape is the same right down to sort of the approximate location of the peak. However, there's a factor of 10 to the 5 here on the y-axis. So their result is larger than ours by about 6 orders of magnitude. And at LHC energies, it's even bigger. So this is sort of a famous result. And it's led to this idea that the glasma is initially produced in a rapidly rotating state. And so there have been many experimental searches to verify this by looking for the polarization of final state hadrons. So it's a simple idea. If you have a large angular momentum, and then, for example, you could have some kind of spin-orbit coupling that would lead to an alignment of the spins with the angular momentum. So yeah, many experimental searches, and the effect has been seen. It's a few percent at RIC. At LHC, as far as I know, the result is consistent with 0. So these very small results are consistent with our calculation. which is basically telling you that the glasma is carrying only a very small imprint of the angular momentum of the initial state. And the majority of that angular momentum is carried by the valence quarks. Okay, so I want to talk a little bit about the momentum broadening of hard probes. And so the idea here is that a hard probe is produced through hard interactions at the earliest phase of a heavy ion collision, and then they propagate through the evolving medium. So we want to look for the suppression of high PT probes, which is called jet quenching. And so this is considered to be a signal for the formation of quark gluon plasma. And the idea is it would require a deconfined state of matter to be able to significantly slow down these super hard partons. And then heavy quarks are particularly interesting because they're sort of rare constituents in the plasma, and then they provide us with sort of a clean probe of the medium. So both energy loss and momentum broadening and hard probes have been studied extensively in equilibrium plasma, but the contribution from pre-equilibrium phases has mostly been ignored. So in order to describe this, we can exploit the fact that there are frequent small momentum exchanges between the probe and the plasma fields, and that allows us to formulate the transport equation in a Fokker-Planck form. So I've written down the equation here. N is the distribution function of the heavy quarks. V is the velocity of the heavy quark. Then this first term here, the curly d, is the material derivative or the drift term. And then there are two collision terms. The second one with this vector y is related to collisional energy loss that I'm not going to discuss. The second one with this tensor x alpha beta is related to momentum broadening. So the momentum broadening coefficient q hat is this transverse projection operator multiplied by the two change of momentum vectors. And that thing can be written in terms of the tensor x alpha beta, which is the correlator of two Lorentz force vectors. So when you substitute in this expression for the Lorentz force and you expand everything out, you're getting the momentum broadening coefficient q hat is written in terms of a bunch of correlators of different components of the electric and magnetic field. And those field correlators are exactly what we calculated, as I explained in the first part of the talk. Okay, so before I show you some results, I want to point out that what we're doing here is quite strange. We're combining two very different approaches. So on the one hand, we have a medium that the hard probe interacts with, and this is a glasma, and we're describing it with a CGC effective theory and a proper time expansion. And we know that this description is valid only at very early times. But on the other hand, we have a Fokker-Planck equation. So this describes the interactions of the hard probe with the glasma fields. It's valid at times that are long enough that the collision terms saturate. So you have a fundamental conflict between the assumptions that set the two timescales for the two pieces of your calculation. And then on top of that, when you do this Fokker-Planck description, you need some gradient expansion kind of approximations. And our CGC approach is assuming boost invariance. So it's not at all clear that you can simultaneously satisfy all of these conditions. Okay, so before I explain more how it works, I'm going to show you the results right away. So this is q hat as a function of time at different orders in the expansion. So if you just look at, say, third, fourth, and fifth order, so that's green, pink, and orange, you can see that they agree with each other fairly well up to around 0.06 Fermi. But the important point is that the saturation regime appears before the tau expansion breaks down. Okay, so then a word of caution here. This figure is obtained for V perp equal to V, and the calculation does not work as well if you allow there to be a substantial component of the heavy quark velocity parallel to the beam. So it's interesting, you can see exactly why that happens. So this is kind of a cartoon of what the glasma looks like at very early times. So the glasma fields are represented by longitudinal flux tubes, these colored tubes here. And the hard probe is this orange blob that's kind of shooting out from the side in a mostly transverse direction. So the idea is we know that the momentum broadening is going to be built up during the time that the probe is in the domain of correlated fields. And at zeroth order, that time is going to be determined by the transverse correlation length, so sort of a width of a flux tube, and the orientation and magnitude of the probe's velocity. So clearly you're going to get saturation faster if the parallel component of the probe's velocity is 0, and this is exactly what we see. So then just a comment here at the bottom, the probe's velocity also enters the momentum broadening coefficient through the Lorentz force. So this is only a very simple picture that can give you the basic idea of how things work at very early times. Okay, so this is a figure that shows what I was just telling you. So we're looking at momentum broadening versus time. Fix b equal to 1, and we'll look at 3 different values of b perp, which means b parallel is increasing as you go down. So the red line are what I showed you before, 4th and 5th order results, and then the orange and the black lines correspond to higher values of b parallel. And so it works exactly as I said, the saturation becomes less and less pronounced as b parallel increases. Okay, so the last thing I want to talk about is the impact of the glasma on jet quenching. So what we want to calculate is the radiative energy loss per unit length of a probe traversing a medium of length L. So this is proportional to the total accumulated transverse momentum broadening, which is given by this formula. So our calculation gave a value of Q max of 6 JeV per Fermi. So it looks big. To see if it's big, we want to compare with equilibrium values. So for a hard quark, PT sort of bigger than 40 JeV, the ratio of Q hat to T cubed is somewhere between 2 and 4. So if we take a value of 3 and we put in some typical temperature, you end up with a Q hat value between 0.05 and 1. So that means that our result for the glasma phase is bigger than the equilibrium result by sort of like a factor of 50, 20, something like that. However, the accumulated transverse momentum broadening doesn't come from Q hat, it comes from the integral over Q hat. And we know that the lifetime of the pre-equilibrium phase is very small. And this is the reason that the contribution of the pre-equilibrium phase to jet quenching is usually ignored. So now we can try to calculate how big it is. So this is a schematic representation of the time dependence of Q hat. So the first phase is the left side of this diagram, where you see a rapid growth to the value of Q max, the 6 JeV per Fermi that we calculated at a time of 0.06. So this is a very rough description of our result. Okay, so you notice that the diagram looks totally different from what I showed you previously, where I was making a big deal about the saturation regime, but that's just because the time scales are so different. So the second part of the diagram is a decrease from T max to T0, which is the time at which hydrodynamic evolution takes over. So this decrease is not captured by our calculation, but it is reproduced by simulations. So we make a simple assumption that it decreases linearly from Q max to this time T naught, and then you can just do the integral and you get this simple expression in terms of the parameters Q max, T max, and T naught. Okay, so the third stage is this hydrodynamic evolution from T naught out to the final time L. And so to calculate the contribution from that part of the evolution, we assume boost invariant hydrodynamics, and then you just get a logarithm. You can do the integral. So then to compare the numbers, we need to put in some values. So using a value of T naught of 0.6 Fermi, and the temperature at which hydro starts is 0.45 JeV. Then we used L equals 10 Fermi, so slightly bigger than the radius of the nucleus, so that the jet is produced close to the surface of the system. Plugging in these numbers, we find that the ratio of the accumulated transverse momentum broadening in the pre-equilibrium phase and the equilibrium phase is about 1. So of course, this is a very rough estimate. It depends on the values of the parameters that you've chosen. But you can play around with the numbers and show that it's not very sensitive to the choices that you make, and it's not very sensitive to the exact shape of that peak. So the conclusion then is that, contrary to what's usually assumed, the glasma in fact plays an important role in jet quenching. Okay, so lastly then you can look at the scale dependence of that result as well. So this figure shows a range of values of QS between 1.9 and 2.1 JeV, where the ratio QS over M is held fixed. And once again, you see that the curve shifts around, but the dependence is fairly weak. Okay, so one last thing one can check. So we formulated our calculation of Q hat in Minkowski space, and it assumes at least approximate translation invariance. But we've calculated it using correlators of electric and magnetic fields that were obtained from a boost invariant ansatz for the vector potential. So to check the consistency, we can see how much the result changes when you change the value of eta, the spatial rapidity. So the red curve here is the curve I showed you before, and the purple and blue curves are larger values of the rapidity. And again, you can see the curve shifts a little bit, but the shape is basically the same. It's not moving a lot. Okay, so then in conclusion, we've developed an efficient method to calculate correlators of electric and magnetic fields using this CGC approach and the proper time expansion. The radius of convergence of the expansion depends a little bit on what you're calculating, but basically it's around 0.5 Fermi. And so I'm just repeating sort of our most important results. We showed that there is a significant correlation between the elliptic flow coefficient and the spatial eccentricity, which means that that initial spatial asymmetry gets transmitted into the momentum field, which is some sort of characteristic of the onset of hydro. We showed that most of the angular momentum of the initial system is in fact not transmitted to the glasma, which contradicts this popular picture of the glasma being produced in a rapidly rotating initial state. And then lastly, we've shown that the glasma plays an important role in jet quenching. So that's all I have. Thank you.
Thank you so much for a very nice presentation. Now we will have some time for questions. So please use the reactions to raise your hand if you have a question. And I don't see any questions yet. So let me start with a question that I had. It's perhaps a very simple and naive question, but obviously when you're doing the tau expansion, there are limitations how far you can go, to which order you are considering. And perhaps it's super naive, but what's the main obstacle to get an exact dependence on tau rather than use an expansion?
I mean, we don't know how to solve the Yang-Mills equation without making some kind of approximation. I mean, analytically, people solve it numerically, but.
So that's exactly what I have in mind. If you can solve it numerically, isn't it better to use some sort of fitting instead of using an pure analytical solution?
I mean, in some ways, yes, it's better, but I mean, we wanted to kind of use a method where we had complete control over the approximations, and that's why we kind of were interested in this proper time expansion. But yeah, I mean, as I said, numerical methods certainly have their advantages.
I see. Yeah, I just didn't understand that subtlety. Okay, any other questions from the audience?
Well, I try my question here. Obviously, beauty quarks are heavy, mentioned here, and strange quarks are light still. But what charm quarks?
So, I mean, the only parameter in our calculation is the velocity of the quark. And so all the figures I showed you were for V equal 1. I mean, we looked at reducing the value of V, but yeah, we're considering ultra relativistic quarks. We considered V equals 1, so the mass of the quark is really not relevant in these results.
So for charm, its range is around 1 GeV.
Yeah. Sorry, I'm not sure what you're asking.
The range is for charm quarks around. I mean, the difference he talks about here, heavy and light here in the region of between less than GeV and up to 2 GeV.
Right. So to see the effects of the quark mass, you would have to look at something like momentum broadening, where the velocity of the quark was not 1.
Okay. Thank you.
Okay. Any other questions? Now, I do have another question related to the Q hat. Essentially, you suggest that pre-equilibrium condition contributes to Q hat essentially as much as the equilibrium phase later on, right?
Right. Yes.
So that does seem to contradict sort of the general assumptions. Am I understanding that right?
Yeah, exactly. It
So-
contradicts general assumptions, but then, one assumes what you can do, sort of.
Right. No, I understand. But now, in light of this new information that you have, how do we go back to the interpretation of the jet quenching in the heavy ion collisions? Does it change the previous picture that we had, that we have quark-gluon plasma, in part because we saw this jet quenching and stuff? Are you saying that essentially it doesn't mean anything about the plasma now? Is that
No,
what
I would say no. I mean, there's, so we had this picture with the flux tubes and how momentum broadening is built up during the glasma phase, but that doesn't mean it won't continue to broaden when you're in the plasma phase. It's different physics going on there, but you're not saying that momentum broadening turns off when you leave the glasma.
No, that's not the point. The point that I'm asking is that since you have so much broadening in the glasma, you don't really need any plasma. And basically some of the early indications or proofs of seeing plasma because of this broadening seem to be invalid.
Okay, but I mean, you're suggesting you could have a glasma but not a plasma.
Well, at
And
least
normally one worries that you never had a plasma at all. You just had a hadron gas.
yeah,
So
yeah.
I don't think we need to worry about that.
Okay.
If I understand you correctly.
Well, I'm trying to sort of exaggerate, but yes, I guess you are.
It seems to me not a concern. I mean, if you're saying that you have a glasma, then you're pretty much happy with that.
Right. Okay. You do create the high density environment, obviously, one way or the other. So that's
You've created a deconfined system of
Right.
colored particles. I think we're happy with that.
Right. Go ahead, Stanislav.
I think that our result only changes the extracted value of Q hat, which is needed to reproduce experimental data. Because people assume that all Q hat which is needed is accumulated during equilibrium phase. And then I don't think that, and since we more or less can estimate what is the Q hat needed to describe the data, we simply assign this to the different phase. But we don't change the picture importantly. And I think that here is extremely simple and nice argument, because calculations are complicated, but the reason why there is this large contribution from plasma is that plasma has very high energy density. So it is the densest phase. And then it's natural to expect that during this densest phase, there is a large contribution to Q hat. Even so, the lifetime is very short.
Okay. Yeah. No. I'm actually, I got that picture. It's pretty clear. I was just trying to see how we reinterpret the data that we know about the plasma. And basically, you're saying that the effective Q hat in the equilibrium plasma could be much smaller than needed before. That's what you're saying.
Yeah.
Yeah, but what would be that value?
Did you hear that, Margaret? Roy
No,
is
I didn't hear
asking,
that.
what would be that value?
Yeah, what is the guesstimate? I mean, how much would that change? I mean, are you saying that it's 90% in this glasma phase versus 5% in the?
So the calculation
what is
we
the
did
number?
says it's about half in each. The contributions are about equal.
Okay. Mm-hmm.
It was the ratio 0.93, but that means that they are roughly the same.
Exactly.
Okay. Mm-hmm.
Okay, any other questions? Any other questions? Well, let me use this moment to actually thank you again for a very nice presentation. It was really a very clear and very nice presentation. So thank you so much.
Thank you, Igor. And thanks for doing this.